second, reproduce the third, and so on, because we ended up making hundreds of these things probably over the last 18 months. And the second thing we wanted to make sure is that there was a reasonable uniform flow through the column. We didn't want to have one column with short circuits down the sides and another column with short circuits through the middle. So we prepared the columns and ran chloride tracer analysis on the columns to see if there was a nice uniform throw, and we were able to hit the bullseye pretty closely with our procedure that we defined. So we follow that procedure now in preparing the columns very closely, very tightly.
Dr. Pierce and his assistant, Jess Everett, will now demonstrate the column packing procedure. Using a long neck glass funnel, a measured amount of soil is added to the columns in 4 1-inch layers. Following the addition of each layer of soil, the column is tapped by hand while it is rotated. The tapping is carefully timed to ensure that each soil layer in every column is packed uniformly. As the sand is added to each layer, the funnel is rotated within the glass cylinder to ensure an even distribution across the surface of the column. Once the soil is completely packed into the column, a measured amount of distilled water is added to completely saturate the column. A measured amount of waste is then added to the saturated column through a funnel inserted through the column top plate. Once the waste is added and smoothed to an even surface, the columns are wrapped in a plastic shield to minimize the degradation of organic compounds by ultraviolet light. The column is then placed in a water bath to maintain a constant temperature during testing. Nitrogen gas is applied to the column at 50 psi to represent overburden pressure in a sanitary landfill. Pressure is maintained until waste stops moving into the column. Standpipes are used to measure the rate of movement of the waste into and through the soil. Liquid effluent from the columns is collected in refrigerated amber glass bottles for measurement and analysis. After allowing sufficient time for the waste liquids to complete their movement into the column is then removed from the water bath and disassembled. The contents of the columns are then removed in layers, starting with the immobile waste fraction left on top of the column, or waste top cake, and continuing with the underlying layers of soil. Each layer is placed into glass bottles and stored for measurement, analysis, or further testing. In a second set of experiments, a clean sand column is packed in the manner previously described. The immobile waste fraction from the first set of experiments is then applied to this column for leaching with simulated municipal waste leachate. This approach permits distinction between release in the primary leachate and release in the secondary leachate. The waste top cake is spread even over the soil surface and then covered with a layer of clean soil. This upper soil layer helps to prevent flotation of the waste components by the leaching media and also ensures that the leaching media is applied evenly across the surface of the waste top cake. A measured amount of leaching media is then applied to the column through the column top plate.
We conducted 2 types of soil column experiments. In the first set of experiments, we concentrated on the physical movement of the waste in the soil environment. We looked to distinguish between the mobile, liquid phase of the waste and the solid portion which stayed on top of the soil. The second group of experiments also included a leaching event in which we leached the solid portion of the waste with a leaching media that replicated sanitary landfill leachate. This leaching media is the same composition as that which is used in method 1311. One of the most interesting results in the first set of experiments was that although the waste moved into the different soils at different rates, the absolute amount that was mobile for the different waste did not differ significantly from soil to soil. In other words, the type of soil influenced the rate of movement, but did not influence the absolute amount of waste left on top of the soil after the experiments were over.
This graph pictures the percent of waste that was immobile in the soil column experiment replicates for each waste. The immobile waste fractions varied from 0 to about 75%, and the experiments were adequately reproducible, especially considering the heterogeneous composition of most of the wastes. Once soil column results were available, the average percent immobile results for each waste were compared with percent solids results obtained using method 1311. This comparison shows that the method 1311 initial filtration step, utilizing a 0.7 micron glass fiber filter, overestimates the immobile waste fraction for 4 out of 5 of the wastes tested. Thus, the current method can underestimate the release of toxic constituents in the primary leachate from certain difficult-to-filter wastes. Here, in a visual demonstration, Jeff Keever is performing the initial filtration step on a waste motor oil. Difficult-to-filter wastes also can clog the filter in the final filtration step, resulting in an inability to adequately separate the waste extract prior to extract analysis. Observe how much of this clearly liquid waste remained inside of the filtration apparatus above the filter.
This method, method 1311, has already been demonstrated to be adequate for a variety of wastes. Oily wastes were not included in this initial evaluation. So rather than to develop a new procedure for these oily wastes, we decided to see if method 1311 would work for the wastes, and if it didn't, see if we can make some relatively minor modifications to the method and still use the existing method. We looked at several different filtration step modifications to solve this problem. We looked at protecting the existing glass fiber either by a pre-coat of diatomaceous earth or sand, or by a pre-filter of coarse glass fiber, or as an alternative a Teflon felt. We also looked at a very novel sintered stainless steel filter that has a different filter structure than all the other filter options we tested. These filtration options were tested and evaluated by comparing them with results from our initial set of soil column experiments.
This graph compares the soil column results with the results obtained with the diatomite filter aid, the Teflon felt pre-filter, the coarse glass fiber pre-filter, the multi-layer filter, and the stainless steel filter. The graph shows that for the range of wastes tested, the sintered steel filter estimated the immobile fraction of the waste observed in the soil columns more consistently than the other modifications tested. In this graph, the immobile waste fraction in the soil columns is compared to method 1311 percent solids results obtained using the 0.7 micron glass fiber filter and the stainless steel filter. Obviously, the steel filter offers significant improvement over the existing filter in estimating the immobile and mobile waste fractions in a landfill environment. The improved performance of the steel filter over the glass fiber filter is due to its unique structure. This illustration diagrams the structure of the glass fiber filter on the left and that of the steel filter on the right. During method 1311 filtration, waste is poured into the filtration device, which is then sealed and pressurized to 50 psi. As the waste moves through the filters, the waste solids remain on top of the filter, and the filtrate drains from the bottom of the filtration unit. The difficult-to-filter waste clogs the glass fiber filter, leaving both solids and liquid on top of the filter. The steel filter completely filters the waste, leaving only immobile solids on top of the filter. The structure of the glass fiber filter is fibrous, with flow paths that are tortuous. Particulate matter can collect in these twisting paths, causing the filter to clog. The steel filter is composed of many small steel beads that are sintered together to produce a porous media structure that has straighter and shorter flow paths through the filter.